Chapter 6, Section 4, Central Limit Theorem. The central limit theorem allows us to use a normal distribution for some meaningful, important applications. So, for all sample size greater than 30, the sampling distribution of the sample mean can be approximated by a normal distribution with mean, mu, and standard deviation. Take your sigma and divide it by the square root of the sample size. So given a population with any distribution that has mean, mu, and standard deviation, sigma, and simple random samples, all of size n are selected from the population. Here's the formula for your z-score conversion. Now, if the original population is not normally distributed, then you cannot use the methods from this section. So if it's not normally distributed, and if n is less than or equal to 30. So you want to check that the underlying distribution is normal, or that the sample size is greater than 30. And we call this adjusted standard deviation the standard error of the mean. So let's take a look at this application. The elevator in the car rental building at San Francisco International Airport has a sign stating that the maximum capacity is 4,000 pounds, 27 passengers. And if you take 4,000 divided by 27, then you get 148. So that's the mean passenger weight, according to the sign. So assuming a worst case scenario in which the elevator is filled with 27 adult males. Now, males have a mean weight of 189 pounds and a standard deviation of 39 pounds. So we want to find the probability that a randomly selected adult male has a weight greater than the carrying capacity average of 148. And then we want to find the probability that a sample of 27 randomly selected adult males, so that would be the worst case scenario, have a mean weight greater than 148. Because if they do, then that would go over the carrying capacity of the elevator. So find the probability that one randomly selected adult male has a weight greater than 148. Well, go to your stat crunch, stats, calculators, normal. And type in the mean weight, 189. And the standard deviation of the weights is 39. And then make sure that your inequality sign is greater than. So all the weights that are greater than 148. Hit compute and you get 0.8534. So an 85% chance, a little more than that a randomly selected adult male will have a weight greater than the carrying capacity. Now notice that the problem says the weights are normally distributed, the adult male weights. So the sample size is 27, n is equal to 27. But since they are normally distributed, we can use the methods from the central limit theorem. So n is equal to 27. And male weights are normally distributed. So that means mu is the same. We have the same mean. Mu is 189. Well, that's actually mu sub x bar. And then our standard deviation is going to be the original standard deviation divided by the square root of n. So that's 39 divided by square root of 27. So about 7.505. Now use that in your stat crunch. Keep the same mean, and let's go with 7.50553 for our standard deviation adjusted. And then compute, and it's virtually certain 0.99999. So we can just round that to 1. So probability that the mean weight of 27 males is greater than 148 is 1. Virtually certain. So notice how I worded that. Using this adjusted standard deviation, the mean weight of 27 males is the likelihood that the mean weight of 27 males is greater than 148 is this probability here. And if the mean weight of the 27 males is greater than 148, then those 27 males all taken together would break the carrying capacity of the elevator, so it's not safe. And there's our graphs from StatCrunch and what we want to plug in here. Introduction to hypothesis testing. Identifying significant results with probabilities. The rare event rule for inferential statistics. So if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, then conclude the assumption is probably not correct if it's significantly less than or significantly greater than. Here's an example about body temperatures. So assume the population of human body temperatures has a mean of 98.6. And now also assume the population standard deviation for temperatures is 0.62 degrees Fahrenheit. So if a sample of n equals 106 is randomly selected, find the probability of getting a mean of 98.2 or lower. So the question is, do we know if the underlying probability distribution for human body temperatures follow a normal distribution? And if you read through the problem, nowhere does it tell us that they do. So it does not say that human body temperatures follow a normal distribution. So no. But can we still use the sample approximations for the mean and standard deviation from the central limit theorem? Well, yes. And the reason is because the sample size is greater than 30. So n is equal to 106, which is greater than 30. So that means our adjusted mean is the same mean, 98.6. And the standard deviation is the 0.62 divided by the square root of the sample size. So let's compute that. 0.62 divided by square root of 106. .0602. So this sentence here, find the probability of getting a mean of 98.2 or lower. We'll write here as probability of x. Lower means less than. So lower than 98.2. Now we can go to StatCrunch and use our normal calculator. So 98.6 and 0.0602. I'll throw in some extra digits, 1972. And then compute. So less than. And this is an incredibly small number here. So set the probability at 0. And the result we're getting is 1.543 times 10 to the negative 11th. I'll just write that down. 0.543 times 10 to the negative 11th. So since the probability is so low, it's reasonable to conclude that the population mean is lower than the 98.6. So in reality, it appears that the true mean body temperature is closer to 98.2. Here's our correction factor for a finite population. So when sampling without replacement and the sample size is greater than 5% of the finite population size in capital N. So that means if N is greater than 0.05 times capital N, adjust the standard deviation of the sample means by multiplying it by this finite population correction factor here, square root big N minus N all over big N minus 1. Let's take a look at this example. So assume that cans of Coke are filled so that actual amounts have a mean of 12.0 ounces and a standard deviation of 0.11 ounces. So find the probability that a single can of Coke has at least 12.19 ounces. So go to your normal calculator and type in 12 for the mean and 0.11 for the standard deviation, and the probability that the volume of the Coke is at least 12.19. So at least means that it could be more. So we want the probability that the volume of Coke in the can is greater than or equal to 12.19. So we set our random variable greater than or equal to 12.19. And then compute. So it's 0.0420. So round that to 0.0421 because of that 5. So for part B, now notice that the problem does not say that the volume of the Coke in a given can is normally distributed. But here we have that 36 cans of Coke have a mean of 12.19. So find the probability that 36 random cans of Coke have a mean of at least 12.19. So that means the sample size is 36. That's how many cans there are. starting off what we know of one can of Coke, we have mu sub x bar is going to be 12, the same mu here, and the adjusted standard deviation will be 0.11 over the square root of 36. Square root of 36 is 6. So we have 0.11 divided by 6, which is 0.0183. So the probability that, let's write this out, 36 random cans of Coke have a mean of at least 12.19. So probability 36 cans have mean greater than or equal to 12.19. So we use our adjusted standard deviation, 0.0183. And then x greater than equal to 12.19. And we get 0 here. So given that result, is it reasonable to believe that the cans are actually filled with a mean equal to 12.0? And if the mean is not equal to 12.0, are consumers being cheated? So it does appear that cans are filled with an amount greater than 12 ounces. So Coke erred on the safe side. Instead of risking cheating their customers, they put in a little bit extra. And that way the cans are statistically guaranteed to always be over the 12 ounces that they advertise. And that concludes this lecture.